Let's dive into a question that sounds like it's straight out of science fiction, but it's happening every single day. How do you teach a machine to move? Not just in code, but in our messy physical world. I mean, really stop and think about that. How do you give a multi-ton metal arm, something with just immense raw power, the delicate precision of a surgeon? Yeah, it sounds completely impossible, right? A total paradox. And yet, this is a problem that robotics engineers are solving all the time. The secret? Well, it lies in an incredibly clever plan. And this right here, this is that plan. Think of it as our journey map. We're going to follow this exact pipeline today, lighting up each piece of the puzzle one by one to see how a robot truly learns how to think. The solution to this impossible problem, well, it has a name. It's the brain, the conductor of the entire orchestra, the maestro behind the metal. It's called MoveIt 2. So what is it? Well, at its heart, MoveIt 2 is a software toolkit that runs on something called ROS2. Now, if ROS2 is the robot's nervous system, then MoveIt 2, that's the brain. It takes all the mind-bendingly complex math of planning a path and avoiding collisions and just simplifies it. It breaks it all down into manageable steps. It is quite literally the thinking engine. So how does this engine actually work? What's going on under the hood? Well, it turns out it follows this surprisingly logical 7-step process every single time it needs to move. And it's a lot like planning a road trip. Seriously, you start with a request. Where are we going? You build a scene and do a collision check. What's on the map? Any traffic? You consult your kinematics, the car's capabilities, and use a planner to find the best route. Then you post-process for a smooth ride, and finally, you execute the plan. You hit the road. The robot's brain does all of this, but in milliseconds. So let's start our journey. The very first piece of the puzzle we're going to light up is the request. Everything kicks off with a simple command. It's as basic as giving the robot a point A and a point B. Here's where you are, and here's where I need you to go. Go. This could be a set of joint angles or a specific spot in space for its hand, but it all boils down to that one simple instruction. Now, what's really fascinating about this next part is that before the robot even thinks about moving, it does something absolutely crucial. It builds a map of its world. This is called the planning scene. It's basically a digital twin of the robot's entire environment. The robot knows its own shape, its own size, and where any known obstacles are. And it's constantly asking itself questions like, okay, if I move my elbow here, am I going to smack into that table? If I extend my arm fully, will I collide with myself? This is the safety check. It's the conscience of the machine. Okay, so the robot has its goal and it knows what to avoid. Now comes the genius part, actually finding a path. This is where complex kinematic models and powerful planning algorithms come into play to chart a course. And MoveIt actually has different strategies for this. On one hand, you have sampling-based planners. Think of these like a scout trying to get through a dense forest. They're just trying to find any clear path as quickly as possible. They're fast, efficient, perfect for a robot that needs to react in real time. But on the other hand, you have optimal planners. These are the engineers. They're not looking for just a path. They're meticulously calculating the single best, most perfect road through that forest. It takes more time and brainpower, but the result is flawless. The choice really depends on the mission. So the planner has churned out a path, a rough draft of the journey. It's basically a series of dots in space. But a robot can't just teleport between these points. The raw plan, it needs to be polished into something fluid and graceful. And this is post-processing. The system takes that jagged path and smooths it all out. It calculates the precise speed and acceleration for every single joint and turns the digital plan into this beautiful, fluid motion. And then finally, it sends those commands to the motors, and the robot moves. Thought becomes action.
So we've walked through the theory, right? The whole step-by-step plan that happens inside the robot's mind. But how does a developer take this abstract concept and actually bring a real robot to life?
Well, it all starts right here with the MoveIt Setup Assistant. This graphical tool is the bridge. It connects the robot's 3D model, its fundamental blueprint, to its new ability to plan. You just load this blueprint, and the assistant gives you a visual way to define everything the robot needs to know about itself, step by step. Inside the assistant, you define what are called planning groups, which is just a fancy way of telling MoveIt, hey, these joints here make up the arm, and these joints make up the gripper. You can set saved poses like a home position and link it all to the physical controllers. And once it's all configured, you click one button, Generate Package. And just like that, the assistant creates the entire set of files needed to bring that robot's mind online. Okay, so we've planned all this in a perfect, static world. But the real world is messy, right? It's unpredictable. So what happens when a new, unknown object suddenly appears right in the robot's path?
This is where we see the true power of dynamic planning. This is where the robot proves it's not just following a static script. No, it has to react to a changing world.
So when an obstacle is added to its planning scene, that entire 7-step process we just walked through, it happens all over again, in an instant. The planner is basically told, your old path is blocked. It then calculates a brand new, valid trajectory that intelligently curves right around the object, making sure the movement is safe and successful. But this brings up a pretty big question. How does the robot know the obstacle is even there, especially if it's something totally new? For that, it needs eyes.
And this is where sensors come in. A depth camera, kind of like one you'd find in a new smartphone, shoots out this whole field of data points, and it measures how far away everything is. This point cloud is then processed into something called an octomap. It's this 3D grid of cubes you see here that represents all the occupied space in the real world. The robot is literally building a 3D map of its surroundings in real time. It can now see and avoid things it never even knew existed.
And there it is, our journey map complete. From a simple request to building a scene, to choosing a planner, avoiding obstacles it can see, and finally, executing a smooth, intelligent motion. Every single piece is connected, all of them working together to turn that construction crane into a surgeon. We've seen how this all works in theory, in a perfect simulation. But what happens when a motor fails? When an object moves unexpectedly? What happens when the robot is pushed to its absolute limits? Well, that's our next story.